Hello and welcome back to the Science of Concrete Materials class. This is lecture number 2. In this lecture, I will present a summary of the class. So it is more like the class in 1 hour. So sit back, relax, and enjoy it. For each topic, though, I might present sample slides from that specific topic just to give you a glance at what is included in the lectures to come. So let's get started. So let's have a quick background and just emphasize why is concrete so important. Concrete is the second most used commodity on the planet, second only to water, of course, for obvious reasons. According to a recent statistic, something on the order of 7 billion cubic meters of concrete are placed every year. That is a lot of concrete. Its versatility and relative low cost made it the construction material of choice. I cannot think of anything we do in our daily lives without the use of concrete. This photo is one of the most impressive bridges in the world, the Tatara Bridge in Japan. Only was possible with the use of concrete. The availability of its ingredients and the ability to mix and form it to almost any shape imaginable made it the construction material of choice. Examples, as you will see, what was possible with the use of concrete. The Palazzo dello Sport stadium in Rome, as you can see, these intricate details, these shapes, it could only be done with concrete. The same thing, this is the Sydney Opera House, which is, I think, everybody is familiar with. Look at these shapes. Also was almost only possible with the use of concrete. Concrete offers many advantages. As seen in the previous slide, it can be formed into any shape easily. It's easy to mix and transport. Also, we can have on-site mixing. It's readily available materials. As I mentioned, relative low cost. It is fire resistant and also durable and low maintenance. There is a caveat here. Only if it is done correctly, then it becomes durable and low maintenance, and we will see throughout the class. Okay, utilizing these great advantages and by availing great deal of knowledge about concrete and its constituents, we were able to make great achievements and meet many challenges: size, height, unusual shapes, and work of arts. For example, the Burj Khalifa in Dubai, which is currently the tallest building in the world. Its core made out of concrete. The Hoover Dam. This Hoover Dam was, constructed between 1931 and 1936, and in October of 2010, the Hoover Dam bypass was opened. As you can see, great achievements with the use of concrete. This bridge in Hong Kong, the Zhuhai Bridge, this is the longest sea bridge in the world, and again with the use of concrete. This is the Palazzo dello Sport stadium in Rome I showed earlier. This is the Sydney Opera House, and again, great achievements were done with the use of concrete. Okay, As concrete offers many advantages and we can do a lot of concrete, however, there are certain disadvantages, or I call them limitations to concrete. For example, sustainability. Although this is a problem that is under our control and we can do something about it. For example, the large carbon footprint, the CO2 evolution. About 5 to 7% of the world production attributed to concrete. This is largely due to the cement production. How can we overcome this problem? By utilizing alternatives to cement, as we can see. The second problem is the depletion of resources. For example, aggregate quarries are running low. What can we do? Look for alternatives to the natural aggregates. And again, we can do something about it. The other problem is the low tensile strength and low ductility. This is an inherent property of concrete, and we have ways to get around it. The volume instability, shrinkage issues, and again, it's under our control, and we can do many things to overcome this issue. As I mentioned, concrete is durable. However, things we need to do as concrete professionals to improve. Again, this problem is under our control. And again, another limitation, its low strength to weight ratio, as compared to structural steel, for example. But again, the many advantages we get from concrete outweigh this issue, for example. Okay, so we have met the challenges of the past, of size and grandeur, as you can see with the impressive structures that have been built using concrete. I am certain we can meet the challenges of the future by making concrete more sustainable and more durable, meaning minimize the impact on the environment and reducing the cost of the maintenance of the concrete structures. In order, again, to decrease the maintenance cost, which are, staggering costs according to recent statistics. And again, as I said, by minimizing the impact on the natural resources and the environment. This can only be achieved by more in-depth knowledge of how concrete forms and how it works at the microstructure level, which will enable us to better select the materials and the mix proportion, use alternative source of materials to reduce carbon footprint and make concrete more sustainable. For example, the use of the supplementary cementitious materials and maybe the use of recycled aggregates to reduce the impact on depleting the natural resources. The second part of the equation of making more durable concrete is the process of mixing, transporting, placing, and finishing of the concrete. By educating the concrete professionals responsible for this part, we can achieve more durable concrete. That will require less maintenance, and so we reduce the cost. This class will provide the necessary information to students to be more knowledgeable about concrete, or in some cases, re-emphasize and reinforce previously attained knowledge, with the end result being better designed concrete mixes and improved practices of mixing, placing, and finishing the concrete. So, what is concrete? Concrete is a composite material. Composite material is a mixture of two or more materials to produce a material with different properties, different meaning from the constituents. Concrete is a composite material that consists essentially of a binding medium within which are embedded particles or fragments of aggregate. In the hydraulic cement concrete, the binder is formed from a mixture of hydraulic cement and water. So let's go back to this slide here. So concrete is made up of cement, which is the most expensive ingredient, by the way. It makes up about 11% of the volume of the concrete. I mean, something on the average between 7 to 15%. Of course, the aggregates, we have the fine aggregates, the sand, and the coarse aggregates, gravel, stone. The aggregates in general make up about 70% of the concrete. Aggregates, of course, for economy and also for volume stability. The next ingredient is water, which is potable water, of course, free of chloride, ions, and other impurities. Water is responsible for reacting with cement to create the binder of the concrete. Other optional ingredients, which is the admixtures. This, is basically the admixture is any ingredient added to the mix other than cement, aggregate, or water. The admixtures, as we will see later, are categorized into two categories: mineral admixtures and chemical admixtures. We will get into that in much more details. Okay, so ingredients 1 through 3 here, as from this slide, are the basic ingredients to make concrete, as I said. The fourth element, which is admixtures, is optional. It is typically used to enhance or improve certain properties of the concrete, such as workability or durability. Some terms that one needs to be familiar with to make sure we know what the distinction is. The paste, when we say paste, that means cement plus water. When we say concrete, that's cement, water, sand, and coarse aggregate. Okay? So those things you have to be familiar with. Okay, how do we classify concretes? What are the types of concretes? There are different classifications. First classification based on the unit weight. Based on the unit weight, concrete can be classified into 3 broad categories. The first is the normal weight concrete, which is the most commonly used concrete, which its unit weight about 2,400 kilogram per cubic meter. The second one is the lightweight concrete. It's in the average or maybe less than 1,800 kilogram per cubic meter. This one is used when there is a desire or a need to reduce the weight of certain structures, mostly used in architectural applications. The third one is the heavyweight concrete. It's larger than 3,200 kilogram per cubic meter. This one is used when there is a need for additional weight, maybe for shielding, maybe for like in nuclear plant structures type, we need this concrete. The second classification is based on compressive strength. So we have again 3 categories here: the low strength concrete, less than 20 MPa or 3,000 psi compressive strength; moderate strength concrete, between 20 to 40 MPa, 3,000 to 6,000 psi; and the third one is the high strength concrete, more than 40 MPa or more than 6,000 psi compressive strength. And again, we need a lot of applications require high compressive strength, as you will see. Okay, In this class also we will study cement in detail, in great detail. As I mentioned, cement is the most expensive ingredient of the concrete and makes up about 11% by volume of the concrete. We will discuss the various cement types coming up, but for now, cement can be classified as hydraulic or non-hydraulic cements. Remember that. A cement is called hydraulic when the hydration products, the cement paste, which is the binder, are stable in an aqueous environment, in water basically. This is the main focus of our studies, the hydraulic cement. But other types of cement will be mentioned in the class. The non-hydraulic cement, the binder in this case is not stable in water. Of course, there are other classifications for cement. The hydraulic cements are further classified, for example, according to ASTM, as Portland cement, which is the most commonly used, and other types such as blended cement, modified cement, and non-calcium silicate cements. The types other than Portland cements, as you will see, are performance-based. Basically, for a certain performance, certain specifications are desired and requested of that cement. We will talk all about classifications of cements, and as I said, in coming up lectures. We will discuss in depth all properties and tests done on cements, including the instrumentation used to do so. We will also study the cement paste in detail, all the tests done on the cement paste, and the detailed microstructure of the paste, and how this microstructure affect the concrete properties. Here is a breakdown actually of what will be discussed in the cement module or cement part of the class. And of course, there are hundreds of slides that will be presented detail on every topic, but in general, or rather in summary, we will define what is cement. We're going to have a historic perspective on the development of cement and how it came to be to the cement we know today. We will talk about Portland cement manufacture, how it's manufactured, the Portland cement composition, the cement types, which is I just mentioned, Portland, modified Portland cement, non-Portland cement, the cement and paste tests that are done for quality control or for controlling certain properties. We will study in detail the cement hydration and the products formed and their contribution, the hydrated Portland cement structure and microstructure, structure of concrete, and the supplementary cementitious materials and the blended cements. All that's going to be discussed in the cement module of the class. So let's just here also mention some quick background about, the history of cement. While cement in one form or another has been around for centuries, the type we use today was invented in 1824 in Britain. It was named Portland cement because it looked like the stone quarried on the Isle of Portland. So this is just, the Portland cement has nothing to do with Portland, and it's a generic name. That's how the name came to be. A gentleman named Joseph Aspdin, who lived between 1779 and 1835, he patented the clay and limestone cement known as Portland cement in 1824. His son, William, actually developed a kiln used to make the first genuine Portland cement. Portland cement was first used in a civil engineering project by Brunel, who lived between 1806 and 1859. This gentleman, Brunel, worked for several years as assistant engineer on the project to create a tunnel under, London's River Thames. Okay, so let's just have a quick look at what will be covered in the cement and its hydration. Portland cement, as I said, is produced by mixing ground limestone, clay or shale, sand, and iron ore. These are the raw materials that then mix together, and this mixture is heated in a rotary kiln to temperatures as high as 1500 degrees Celsius. The heating process causes the materials to break down and recombine into new compounds that then can react with water in a crystallization process called hydration. This is a schematic of a kiln here. It shows what happens in the kiln. So the raw ingredients of the Portland cement, are, as I said, iron ore, lime, alumina, and silica is fed into this kiln, which is an inclined rotary structure measuring up to 200 meters. Of course, modern kilns are a bit different, but this is just the basic process. These materials are ground up and fired in a kiln to produce clinker. And you see here, these are the various zones and the processes that happens in each one: dehydration, calcination, clinkering, and then cooling. And after cooling, the clinker is finely ground after that. Of course, gypsum is added to the ground clinker, and after that it becomes Portland cement. Before gypsum is added, it's just clinker. Okay, so these are the major phases that really make up the clinker. We will get into this notation later. The main phases are the tricalcium silicate, shorthand written as C3S, dicalcium silicate as C2S, tricalcium aluminate C3A, tetracalcium aluminoferrite C4AF. As I said, we will look into this shorthand notation in a bit. And again, okay, I'll mention it here just since we talk about it. When we, in cement chemistry shorthand, when we say A means the alumina, which is the Al2O3, C means calcium oxide, F means ferric oxide, H means water, S means silicon dioxide, S bar means the sulfur trioxide or sulfate, the M means the magnesium oxide, MgO, the Na2O equivalent, which is the alkali content. And these are the phases in the cement: C3A, tricalcium aluminate, C4AF, tetracalcium aluminoferrite, C2S, dicalcium silicate, C3S, tricalcium silicate. The CH means calcium hydroxide, CS bar H2 means gypsum, and the C dash S dash H means calcium silicate hydrate. Just quickly to become familiar with these terms. We will go through these in more in details later. Okay, so back again to the cement types and how they are classified again. And again, as I said, we will study in depth the cement types. Many types of the cements are produced to suit many applications. There are 5 basic types of Portland cement in use today. The type 1, general purpose cement. Type 2, by the way, these are a classification according to ASTM C150. Type 2, which is the sulfate resistant cement, used when concrete is in contact with high sulfate containing soils. Type 3, high early strength, which gains strength faster than type 1. For example, enabling forms to be removed sooner if we need strength quickly. Type 4, this is low heat of hydration. For example, for use in mass concrete structures such as dams or large sections. Type 5, the severe sulfate resistance. When the sulfate concentration in the soil above a certain concentration, type 5 almost is a must. As I said, other Portland types will be discussed. Non-Portland types also will be discussed. So here's like a summary of the cement types according the five types I just mentioned. According to ASTM C150, ordinary Portland cements. These are the 5 types, and a brief description of their properties and when they are used. Here's the remainder of the types. As I mentioned, there are something called the modified Portland cement. Don't worry, we will discuss all this according to ASTM C1157, the performance type cements, hydraulic Portland cements. And also we have blended cements. These are blended with supplementary cementitious materials according to ASTM C595. We have expansive cements. Sometimes again, we can put these into really good use. We have special cements for certain applications like rapid setting cements, white cements, masonry cements, or oil well cements. And again, we have also non-Portland inorganic cements, like the calcium aluminate cements and the gypsum plaster. That's what we will study. Okay, what we will study also the hydration process of the cement and how it relates to the end user and what it means to the concrete professional, each stage of these. The stages of hydration. Once we add water, then for a period, it's referred to as the dormant period right here, and what forms, what happens in each stage. Then we have this, what's called stage 3 and 4, the acceleration and deceleration stage. Stage 5 called the steady state stage. And again, we will discuss what happened, what forms in each stage, and what every stage means to us about, for example, right here we can transport, place and finish the concrete. Right here, strength gain starts right here, and the hardening. And after that, what happened, how the reaction slows down, for example, and what needs to be done, curing, and so forth and so on. This is just, a quick glance at the hydration process and what happens when the cement comes into contact with water. Okay, and of course we will study the hydration products, what forms, like the calcium hydroxide or the calcium silicate hydrate gel I mentioned. We have the sulfo-aluminate phases, referred to as the monophases or the ettringite. There are other products such the aluminate hydrate phases, and how the formation of these hydration products over time leads to stiffening, the loss of workability, setting, the solidification, and hardening, which is the strength gain. And again, we will study all that in details, what happened and why, how and why it happens. Just this is, a sample slide of what will be presented. Of course, again, we will look at the microstructure of the hydrating cement paste. What do you mean by structure anyway? Structure means the amount, size, shape, and distribution of phases present in this hydrating cement paste. The macrostructure is what can be seen unaided, which is anything larger, 200 micrometers or larger. The microstructure, it's something that must be observed with the aid of a microscope. As you can see here, this is, enlarged several thousand times. It enables you to see at this level what are the products and how they look like. And of course, all this we study because that's really what affects the concrete properties from an end user perspective. We need to know this. We need to know this. And again, also big part or a major part of this class is the supplementary cementitious materials, which is basically the mineral admixtures. These are, the addition of finely ground solid materials to concrete is an established practice in modern concrete technology. These materials are called mineral admixtures or supplementary cementitious materials, SCM. These admixtures with the mineral component is being used primarily to replace cement. Remember what I said about sustainability, and we need to come up with an alternative to the use of cement for various reasons. This is one of them. These are added for a variety of purposes. As I said, to make concrete more sustainable. On the other hand, we can improve the properties, improve the workability of fresh concrete, enhance the durability of the hardened concrete. That's what we gain from the use of these materials. It's really a great addition to concrete technology, in my opinion, and it should be utilized more and more. Okay, so examples of these, supplementary cementitious materials, these such as the pozzolans, such as fly ash, metakaolin, slag. We will study their origin, makeup, and how they benefit concrete. The mineral admixtures, can be classified into three main categories. Pozzolanic materials, cementitious materials, and non-reactive materials. These materials typically, the first two categories are either, used as blends with the Portland cement to form one product, blended cement. This practice is more common in Europe than in the US though. Or it is more common in the US. These materials are added by the concrete producer to mix as a supplementary cementitious material. The result in either case, whether it's blended with the cement and bagged, the cement sold as blended cement, or these are added by the concrete producers, the result is the same. These mineral admixtures, they interact chemically with the hydrating Portland cement to form a modified paste structure. So some of the classifications, of course, we will study. As I said, the materials. These materials can be pozzolanic materials, non-cementitious pozzolanic materials. Properly, they form with certain products of the hydration, certain products of the hydration process to form new products and enhance concrete. Such as I said, silica fume, metakaolin, rice husk ash. These are called highly pozzolanic, normally pozzolanic, such as the class F fly ash. The other category, they can be cementitious. They offer cementitious property and also pozzolanic properties, such as slag and class C fly ash. Of course, the cementitious material, it's the Portland cement. And again, don't worry about this. We will discuss this in detail. I'm just showing this slide as an example. We will go over it. Of course, again, we will go over, for example, how these materials, where they come from, how they are produced. A lot of these materials are byproducts of other industries. So by using it, with the exception, for example, of the silica fume, they are less expensive than cement. And also we end up reducing the impact on the environment by using them. We will see where they come from and what industries they come from. And of course, we will study their physical and chemical properties, what their makeup. For example, on this slide I'm showing here the X-ray diffraction, XRD analysis of slag. What is it made up of, and why is it of benefit to us? Okay, we will go through all that. And of course, we will detail the impact or the contribution of each of these supplementary cementitious materials on the properties of concrete, how they impact concrete, and what benefit we get from them. And again, all this will be presented again. I'm just showing this as to give you a taste of what's to come. Okay, so also we will discuss, once we finish the cement module, we will go to the concrete properties. For example, the fresh properties of the concrete. As I said, all properties of the concrete will be discussed, fresh and hardened properties. The significance of all these properties and how they will impact the concrete during its service life. For example, fresh properties. As I mentioned earlier, the properties of concrete during its service life, strength and durability, are greatly impacted by the process, by the concrete processes, mixing, placing, and finishing of concrete. That's why fresh properties of concrete are of great importance, and thorough understanding of these properties is essential for engineers and supervisors in the field. So the properties we will be looking at and understanding, the workability, for example, which, workability will have related issues such as segregation, bleeding, slump test, which is a measure of workability. Set-in time is another property we will look at. Air content, how we measure air content, and you will see why is that important. Unit weight and yield, and plastic shrinkage. So again, workability, as I said, the property of freshly mixed concrete that determines its working characteristics. That's definition, meaning the ease with which it can be mixed, placed, compacted, and finished. We will look at the factors affecting the workability, method and duration of transportation, for example, quantity and characteristics of cementitious materials, the consistency of concrete measured by the slump, aggregate, grading, shape, surface texture, percent of entrained air, water content, concrete, and ambient air temperature, the use of admixtures, if any. That's what's impact properties, almost everything. A good indication of the water content of a mix and the workability can be had from a standard slump test, as you can see, and a lot of you are probably familiar. Most concretes, let's go back, sorry. Most concretes mixes, have slumps in the range of 2 to 5 inches. And again, we want to avoid segregation. So as I said, freshly mixed concrete must be relatively easy to transport, place, finish without resulting in harmful segregation. So we need a workable mix. The material has to be almost fluid-like, and it has to be cohesive. Okay, so it is really a qualitative property that incorporates consistency, ease of flow, and cohesiveness, meaning it does not segregate. Okay, and as I said, the benefits of workable concrete mix cannot be overstated. Having mixed with the right workability will ensure that concrete is placed, compacted, and finished properly, which eventually contribute to the strength gain and durability of concrete. Learning what needs to be done to have a workable mix, appropriate for a specific application, will go a long way in improving concrete properties over time. Adding water on site to improve workability is not one of them, and this should be avoided at all costs. It should be avoided. Okay. So if we want to have durable concrete, we must avoid segregation. Segregation, basically, if we define it, is the separation of the components of fresh concrete, which will result in a non-uniform mix. Now, as concrete is made up of materials of different size and specific gravities, so incorrect handling, mixing, place, and consolidation more than likely will result in segregation. Basically, so for example, dropping concrete from height without proper conveying method will result in segregation. Segregation will result in defected hardened concrete, which will lead to decrease in strength over time. Okay, and most importantly, will adversely affect the integrity of the matrix, making it more permeable and prone to the ingress of harmful elements. And again, we will learn in subsequent lectures about environmental impact and the durability issues such as sulfate attack and corrosion and all that. Okay, so segregation, as you can see in this slide, that's what poorly consolidated concrete, this photo right here, and this is properly consolidated concrete, and you can see the difference easily. Okay, so the segregation is impacted by basically the gradation of the aggregate, which including the maximum size aggregate and the fines. So basically, larger maximum aggregate size and less fine will increase the likelihood of segregation. The particle shape and texture also impact segregation. The water cement ratio also impacts segregation. And again, don't worry, we will go through all this, these properties in details. I just mention here just some highlights of what we will be talking about. Of course, bleeding, another issue we will talk about. What is bleeding, how to control it, and the air content of the concrete, and the various other properties. Okay. The next topic we will discuss is the aggregates. We will study aggregates in great details. Okay, we will look at their classification. Classification of aggregate, geological origin, size, weight, the properties of aggregate: shape, texture, size, gradation, moisture content, specific gravity, bulk unit weight. And of course, eventually, all this we need to understand the effect on concrete properties, fresh and hardened. And again, all this will be discussed. So all these properties will be important for a suitable mix design. Okay. Okay, and again, following that, we will study the mix proportioning, the mix design. As you can see here, these are just examples of the proportions of various mixes. Cement, water, air, fine aggregate, coarse aggregate. You see, it varies here. And again, all this, of course, in case of air-entrained concrete or non-air entrained concrete, all this will be done for reasons. Why? We'll understand why and how to design a certain concrete mix. So basically, what I will be presenting in this class is the ACI method of design, which is, basically it's a methodical, step-by-step process. For example, determining the job parameters, aggregate properties, maximum aggregate size, slump, water cement ratio, the use of any admixture. Then after that, we calculate the batch weights. Then we make any adjustments of batch weights based on trial mix, made according to these calculations. And again, we will make any adjustments. And again, this is just an example of what how the variables affect the properties of the concrete and what they mean to you as a mix designer. For example, you could see the strength has an inverse relationship with water cement ratio. In order to increase strength, we need to reduce the water cement ratio. The cement is the most expensive constituent of concrete, as we said, so more cement means costly mix. Workability, which we discussed earlier. Workability, it has many implications on the durability of concrete later and its relationship with water. Of course, workability increases with the increase in the water content, but that will have negative impact on durability. So we have to look for alternatives, how to really get more workable concrete, better workable concrete, while we maintain in water content lower, okay, in order to get good strength. All this will be discussed. This is basically a summary of the process, what goes on. Like I said, it's a methodical process, but nonetheless, it's not just punching numbers. You need to understand many things in order to be able to manipulate the process and come up with a good concrete mix. Okay, then once we finish that, we will go to the next module, which is the chemical admixtures. As the need to modify concrete properties, in the fresh and hardened states. This resulted in the growth of the use of admixtures. There are hundreds of products being marketed nowadays. Construction engineers, must know about admixtures, their advantages and limitations. it is estimated that in some locales, almost 70 to 80% of concrete produced contains some kind of an admixture. I cannot think of any mix that I have used did not contain admixture. So the students, will be provided with a comprehensive knowledge about chemical admixtures and their impact on concrete properties. Okay, sorry, I went too fast. So we will study, the classification of chemical admixtures, like the air entraining agents according to ASTM C260. This one basically to improve the resistance to concrete to freezing and thawing. The set control and admixtures, this one control basically setting, either accelerating and induce early strength, or retarder that delays the set for various reasons. Plasticizing admixtures, this one, these are water soluble polymers, basically designed to enhance workability by increasing the slump without increasing the water content. Okay, or sometimes rather than just increasing the slump, we could reduce the water content for a desired workability. There are other miscellaneous admixtures that we will also discuss for special applications. This is just an example of the classification of ASTM C494. It defines these 5 different categories of admixtures. We will go through them in detail, don't worry. Okay, this is just an example, sample slide of how these air entraining admixtures, what they do to enhance the cement paste and eventually the concrete performance in freeze-thaw environment, in cold climates, to make sure we mitigate the potential of shrinkage due to the freezing water within the concrete. We will talk about it. Okay, after that we will move to the next module, which is the concrete response to stresses. As you know, before we study the hardened concrete, mechanical properties such as strength and modulus of elasticity and all that, we need to understand how concrete responds to stress. It's concrete, as you can imagine, concrete is really a complex heterogeneous material. It's not homogeneous material like steel, where the properties are easy to understand. It's different. So its response, concrete response to stress, depends on the response of the individual components that make up the concrete, and also on the interaction between these individual components. So basically we will go through this, but before we study the concrete properties, we will basically have a refresher on the stress strain curve in general, the modulus of elasticity, the proportional limit, the Hooke's law for general, not particularly for concrete. We will introduce this, but we know concrete does not behave in this manner shown in this diagram, but we will study this as an introduction. And of course, and again, we will reintroduce you to the various different terminology of mechanics of materials, what are the terms and what they are, before we get into the concrete. Then we will study and explain how, because as I said, let me back up, concrete is not a heterogeneous, homogeneous material. So determining, for example, the modulus of elasticity is not a straightforward approach. We will explain how the modulus of elasticity, for example, is determined, and the models that were developed by the various researchers over the years on what is maybe the best way to model the concrete in order to develop formulas for the calculation of its modulus of elasticity, for example. All this will be discussed in the response of concrete to stresses. Of course, we will look into the response to biaxial stresses and how the concrete in biaxial loading concrete strength can be increased and what that means to us. Maybe we will look at the response to multi-axial strain stresses. We will look into that maybe in briefly, but these are some of the topics we'll be discussing. Okay, after that we will get into the concrete testing. The concrete properties, the hardened concrete, after we have gone through the response to stresses. For example, we will look at the main, properties of hardened concrete, the principal properties such as strength, permeability and durability, and volume changes, shrinkage, creep, and all that. So as I said, compressive strength is, most important because it is easy to measure. Concrete is mostly loaded in compression in real life. It is typically and strictly speaking indicative of other properties. So we will have a lot of emphasis on compressive strength measurement. It is, measured using cylinders or cubes loaded axially. Of course, we will talk about them in details. Also in this module, we will introduce standardized testing, the significance of testing. Although test samples do not entirely necessarily represent the structure, but we will talk about all that. And again, we will study the compressive strength, tensile strength, flexural strength, modulus of elasticity, and we will look at some of the non-destructive testing. This is how compressive strength is measured. As I said, this is almost one of the most significant tests because this property is indicative of other properties. It's straightforward. As you can see in this machine, it's loaded axially, and then the strength is recorded, and a curve like this is drawn. We will look at what affects each property. As you can see here, with all these factors affecting the compressive strength, it's easier to ask what doesn't affect strength than what does. We will look into that. And again, we will look at the tensile strength test, which is the split-in cylinder test. There is no standard testing for tensile strength of concrete, but this test per STM is acceptable, and we will look into it and how it's done and what affects it. We will look at the flexural strength of concrete to determine the modulus of rupture, and again, we will look into this in details. After that, after this, we will move to the next module, which is the basically the time-dependent deformation, which is the volume instability of concrete, which really this is a big deal. And understanding in details these issues will help every engineer. So we will have an introduction. We will look into drying shrinkage, carbonation, autogenous shrinkage, creep, and thermal shrinkage. These are the major issues affecting time, comprising time-dependent deformation. Of course, as I said, studying the cement paste and how it develops and microstructure and its porosity, the type of pores, we will look into details. And again, this is a sample slide. We will look into details and understand why, for example, drain shrinkage occurs, and at the microstructure level, the evaporation of water from which pores causes what type of shrinkage. Knowing this, and again, will help every engineer, knowing, for example, how to protect the concrete after pouring, to cure it properly, and the many things that the engineer needs to do or not to do in order to make sure long-term concrete functions properly. So understanding again at the microstructure level what happens in the concrete, what causes the concrete to shrink in every situation, I am sure this kind of education and awareness will make engineers better engineers, in my opinion. After this, we will have I think the last module of the class will be the durability. And again, durability is the second part of the equation. Concrete strength. Let me go back. I'm just going fast here. Concrete strength is one aspect. The second part of the equation, durability. We need concrete to be durable and less expensive to maintain over the years. So a durable concrete is the one which will withstand to a satisfactory degree the effects of service conditions to which it will be subjected. Okay? As I mentioned earlier, concrete is durable material. It is one of the advantages of concrete, its durability, but only if it's done correctly. Meaning if we fail to address certain shortcomings or limitations of the concrete material, durability will be compromised, the result being staggering repair costs and lost profits from non-used structures and so forth. So we will learn about the durability issues, as I said, how to identify them, what causes them, how to mitigate them. This, of course, comes from the understanding, as I just mentioned, at the microstructure level. In order to verify and confirm damage, we need to examine the microstructure of the concrete for evidence of telltale signs. So the knowledge of the microstructure of undamaged, concrete is essential to compare it to what happens in the damaged concrete. The damage, cracking, for example, before it manifests itself at the macro level, it would have originated at the microstructure level. For example, in the case of the alkali silica reaction, the alkali silica reaction product may be present in the interfacial zone between the concrete, between the paste and the aggregates, for example. Or for example, the presence of ettringite and the cement paste, could be the cause of damage or cracking. In some cases, the indication of the damage could be visible at the micro level, such as the case of efflorescence and leaching. The trained eye, in some cases, will be able to identify the cause of damage due to the certain telltale signs. So basically, again, this knowledge is essential. So the engineer is really equipped of the tools and the knowledge in order to identify certain types of damage. First of all, we need to prevent it. Let me re-emphasize, prevent it by good practices of good mix design, proportioning, good concrete practices in the field of placing, finishing, curing, etc. And the third thing is the engineer should be knowledgeable to be able to identify, for example, certain telltale signs of certain damage, identify them early, and make sure we mitigate them before they manifest into something harder to control or will be more expensive to repair. So the major factors of damage we will be looking at, first of all, we need to understand, as I mentioned earlier, if you remember, the segregation. When we have segregated concrete, the concrete becomes, we compromise the integrity of the concrete. Concrete becomes more permeable, will allow the diffusion of other unwanted elements into the concrete, which will cause other forms of damage. So we will study permeability, diffusion, the leaching and efflorescence, why it happened, what causes it, the carbonation, alkali-silicate reaction, sulfate attack, corrosion, and freeze and thaw cycles. These are the major durability issues. This is, for example, a slide from the alkali-silicate reaction lecture. The mechanism of it, how it happens, what really needs to happen in order for this alkali-silicate reaction to take place and damage the concrete. You understand this, you are better equipped to mitigate it. The corrosion, why the corrosion happens and what can be done to prevent it or actually minimize its damage. The freeze and thaw, I think we will look at this, how, where, why freezing occurs, and what can be done to minimize or mitigate its effect. And again, lots of information will be presented in this class, and just to present the level of knowledge required by the engineers and the students in order to, as I said, be better equipped to deal with these issues, and basically to produce more durable concrete. Of course, we will talk about this in the freeze-thaw cycle. What happens during freezing? What could happen and what needs to be done in order to prevent it? Okay, so these are the main modules I just finished that will be presented in the class. Another part of the class, these processes I'm going to talk about now may not be presented later in the class, but I'll talk about them now. And I will see if there is a need, we may do a lecture about it. So basically, let's talk about the processes, basically mixing, placing, finishing, and curing. Okay, so like again, since the properties of concrete are also impacted by the processes, I said mixing, placing, etc. It is important to understand what are the do's and don'ts in the field. Okay, so let's talk about mixing. The aim of mixing is to blend all the ingredients of the concrete to form a uniform mass and to coat the surface of the aggregates with cement paste. We have the ready mix concrete, and this type, ingredients are introduced into a mixer truck and mixed during transportation to the site. So we have it wet, where the water added before transportation, or dry, water added at the site. This is a schematic of a ready mix plant. As you can see, just a schematic. I'm sure many of you are familiar with how the process works. So we also have site mixing, either by hand or by a mechanical mixer. I mean, this is for very small applications and something like this. But again, this is one of the advantages of concrete. It can be mixed in different ways, making it convenient at times. So mixing time should be sufficient to produce a uniform concrete. The time of mixing depends, on the type of mixer and also to some on properties of fresh concrete. Okay. So we want to avoid undermixing, which will produce non-homogeneous concrete, or we want to avoid overmixing, which will run the danger of water loss or breakage of aggregate particles, for example. So something that has to be basically looked at. The second process is the consolidation. The process of compacting concrete, consists essentially of eliminating the entrapped air within the concrete. So inadequate consolidation can result in honeycomb, excessive amount of entrapped air, voids, which is referred to as bug holes, placement lines, these called joints. So that's consolidating concrete properly is essential to avoid any of these issues. Consolidation can be achieved by basically vibration. This is typically in thicker slabs and reinforced beams and columns where it's congested, so vibration is essential here. Tamping and rodding, this is for flat work such as sidewalks that is not congested like beams and columns. Okay, vibrators. So vibrators can be, external or internal vibrators. Internal vibrators, the pokers are immersed into concrete to compact it. The poker is easily removed from point to point. The external vibrators, these are clamped directly to the formwork. These will require strong, rigid forms. So, and again, before using external vibrators, you better make sure your form can handle it. You don't want to end up with a disaster there. Okay, so what really affects the selection or the of the vibration process? So, for example, internal vibrators, we need to know the diameter of the vibrator and the vibration radius action. And this information, again, from experience, from the vibrator supplier can tell you how to be placed. This is, for example, from ACI 309. This shows the recommendation of the diameter of the vibrator, the radius of action, and the frequency of the vibrator, and the rate of placement. So this is a good table here in case you need some more information. Okay, so about vibrators. So this photo shows you the concrete workers here are using vibrators. So let's go let me talk more about vibrators. The vibration must be systematic. Correct vertical penetration, a few inches into the previous lift, which has not solidified yet. Otherwise, it defeats the purpose. This is of systematic, regular intervals. This will give adequate consolidation. Incorrect random penetration of the vibrator at angles different from vertical and spacing without sufficient depth will not ensure bonding of the successive layers. And again, this is something engineers and supervisors in the field must make sure that happens. Otherwise, the results are not good. And I have seen a fair share of this investigating certain structures about poor consolidations and poor vibration. So to aid in the removal of the trapped air, the vibrator head should be rapidly plunged into the mix and slowly moved up and down. And again, there's a method of using these. The concrete workers must be trained and must have the knowledge on how to use them. It's not a random ad hoc process. So the actual compression of vibration is judged by the appearance of concrete surface, which must be neither rough nor contain excess cement paste. Okay. This is as I said, a picture of concrete workers using vibrators. Okay, so now the external vibrators. These refer to as form vibrators. There are vibrating tables, but usually maybe used in the lab. Sometimes actually used in precast for certain flat precast elements. Form vibrators, though, are rigidly clamped to the form work, so that both the form and concrete are subjected to vibration. A considerable amount of work is needed to vibrate the form, so you must be aware of that. Forms must be strong and tied sufficiently to prevent distortion and leakage of the grout. And again, if you do not have experience or knowledge, consult somebody who does. But in many cases, we used form vibrators due to congestion or due to, for example, height, where you do not have long enough vibrators to reach, for example, the bottom lifts of a retaining wall that may be several meters high. So the use of form vibrators is common in these cases, but again, somebody with experience must be in charge. This is a photo here of using form vibrators, and again, mostly used in walls because the reach is not that easy to the bottom of the wall. Okay, curing of concrete. I couldn't really emphasize this topic more. Concrete must be cured properly. Properties of concrete can improve with age as long as conditions are favorable for the continued hydration of the cement. And again, when we study the cement hydration, you will appreciate this and you will understand why curing is so important. Okay, so these improvements are rapid at early ages and continue slowly for an infinite period of time. Curing, again, is the process used to promote the hydration of cement and consists of control of temperature and moisture movement from and into the concrete. So the hydration reactions can take place in only saturated water-filled capillaries. We will see what that means in the cement module. So why cure concrete? Curing serves two main reasons. It delays dry and shrinkage until concrete is strong enough to resist shrinkage, and also it, as I said, it promotes and continues the hydration process. So curing methods, which apply additional water to the surface of the concrete during early hardening stages, using wet covers, sprinkling, ponding, or other methods that prevent loss of moisture from concrete by sealing the surface, like waterproof plastics, or the use of liquid membrane, or curing compounds referred to, or for example in cases like forms left in place, like the case of a column. Methods that accelerate strength gain by supplying heat and moisture to the concrete. This is mostly used in the precast process, by using live steam curing. So this one here, a graph which shows you really the importance of curing, or what curing rather, because look at the different methods. how they affect the strength gain. You know, this is here age in days, and this is the compressive strength. Look at this first curve here. In laboratory, air entire time. In air, after 7 days moist curing. After 28 days moist curing the entire time. Look at the difference. Curing really goes a long way. And as I said, I cannot emphasize to engineers and supervisors in the field the importance of curing. What curing that is, when of course, when it is, in certain cases, curing compound is used, but what curing is essential in many cases, and I recommend it. Okay, so basically this is the end of this lecture number 2, the summary of the class. I know it is long, but really basically I wanted to pack as much information as I could in this lecture in order to give you basically a taste of what to come and what we will discuss in this class. It's really a jam-packed class. It's a university level class with all the information that you will require about concrete and cement. So I hope you watch my class, and again, I hope you will give me any feedback that you will think will be productive in order to improve or to know something I was not aware of, for example. Whatever the case is, I don't mind comments and feedback. So again, thank you for watching, and next time we will start on the cement module. So see you next time. Thank you.